They're the silent rulers of a world most of us rarely get to see. And they're not just swimming around. They are the pioneers of the vertebrate blueprint, the absolute architects of aquatic life. So today, we are diving deep into the incredible story of fish. I mean, just look at the sheer scale of life on our planet. It is an absolutely incredible tapestry of organisms. But for this explainer, we're going to zoom in on one particular group, a group that literally laid the foundation for every backboned animal out there. Yeah, including us. And the diversity? It's just staggering. I mean, you've got everything from the totally bizarre, slime-producing hagfish hiding out on the ocean floor, all the way to the perfectly streamlined shark, a true apex predator of the open sea. They've managed to adapt and conquer just about every single aquatic environment you can imagine. And you know, this diversity isn't just about pretty colors or weird shapes. No, it's about finding really complex solutions to the tough challenges of living underwater. Things like buoyancy, breathing, moving. Their adaptations are, honestly, nothing short of an evolutionary masterclass. All right, let's get into it. Here's our roadmap for today. We'll start at the very beginning with the first vertebrates. Then, we'll meet the cartilaginous predators, witness the incredible rise of bony fish, and break down all their amazing adaptations. And stick around because we'll wrap up by connecting their story to our own. Okay, so our journey starts way back. I mean, long before the dinosaurs. We're heading into the deep past to meet a group of pretty strange, jawless creatures. These guys were the original pioneers of the vertebrate body plan, and they really set the stage for, well, for everything that came after. So, let's put that into perspective. We're talking about going back over 500 million years to the Paleozoic era. This was a time of just explosive diversification in the oceans. And this is when the very first fishes show up in the fossil record. We call them agnathans, which literally just means without jaws. Now, this group included some pretty wild, heavily armored critters called ostracoderms, but, and this is the important part, they were also the ancestors of the jawless fish that are still swimming around today. Right, so these modern-day survivors, the hagfishes and the lampreys, are grouped together in what's called a clade. And a clade is really just a group of organisms that we think evolved from a single common ancestor. So these guys, the Cyclostomata, they're like a living, breathing link to the deep past. They give us this incredible window into the biology of the very first vertebrates. And this is where it gets really interesting. You've got these two groups using the same basic, ancient toolkit, but for totally different survival strategies. On one hand, you have the hagfish. They're deep-sea scavengers, almost blind, and they find their food with an amazing sense of smell. And for defense, they can produce liters of this suffocating slime in just seconds. It's wild. Then you've got the lampreys. Many of them went a completely different route. They became parasites, latching onto other fish with this toothed, funnel-like mouth. Their life cycle is also pretty complex, with a long larval stage that filter feeds in freshwater streams. So, what's the big takeaway here? Their design is fundamentally primitive. I mean, they're missing all the features we just take for granted in most fish today. No jaws, no paired fins for steering, no protective scales. And their skeleton isn't even bone, it's cartilage. Their main support is a persistent notochord. And get this, that's the same flexible rod that runs down our own backs when we're embryos, before our vertebrae form around it. So this whole world of jawless filter feeders, scavengers, and parasites, it was about to be completely turned upside down. I'm talking about one of the single greatest innovations in the entire history of life on Earth. Any guesses what it was? Jaws. It was jaws. And they changed everything. In what is just a classic example of evolutionary tinkering, the skeletal supports for the first gill arch, structures that originally just helped with breathing, got repurposed. They were modified into a hinged jaw. And just like that, vertebrates went from being passive bottom feeders to active predators. Suddenly, they could grasp, bite, and crush food. This opened up a whole new world of possibilities, triggering a massive explosion of diversity and giving rise to a new group, the gnathostomes, which literally means jaw mouths. So this incredible innovation leads us straight into our next chapter. The first major group of jawed fish to really take over were the chondrichthyes, and they had a new strategy. They traded in all that heavy bony armor for something completely different, a lightweight, flexible skeleton made entirely of cartilage. And this cladogram, this evolutionary family tree, it shows that exact moment perfectly.
This is a huge fork in the road. The jawed vertebrates split into two massive lineages that honestly still dominate the waters today. On one side, you have the chondrichthyes, that's your sharks, skates, and rays. And on the other, the osteichthyes, the incredible dynasty of bony fish. This split was a fundamental choice in building materials, and it led to two totally different sets of adaptations.
Now, if we zoom in on the biggest group of cartilaginous fish, the elasmobranchs, we see two winning body plans emerge. First, you've got that classic shark shape, what we call fusiform. Think of a torpedo. It's all about speed and power in the open ocean. And then you have the completely different design of the ray. It's dorso-ventrally flattened, basically squished from top to bottom, making it perfectly adapted for life gliding along the ocean floor. And this table just lays out their different evolutionary paths so clearly. Take the pectoral fins. In sharks, they're mostly for lift and steering. But in rays, they become these huge wings that they use to fly through the water. And check out the gill slits on the side of the head for sharks, but tucked underneath on the bottom for rays. Even the tail is different. Sharks have what's called a heterocircle tail. It's asymmetrical, and that powerful upper lobe gives them both thrust and lift. It's just a perfect example of how evolution can take one basic blueprint and adapt it for totally different ways of life. So what makes them such an incredible predators? Well, their toolkit is just amazing. Their skin, for instance, is covered in what are called placoid scales. They're basically tiny teeth, and they're engineered to reduce drag in the water. Then there are their senses. They've got a lateral line system to feel vibrations from a distance. And get this, they can sense the tiny electric fields given off by their prey using special pores on their snout. It's like a built-in superpower. And one more crucial thing, they don't have a swim bladder for buoyancy. Instead, they rely on a huge, oily liver to keep from sinking. All right, so let's jump back to that fork in the evolutionary road and follow the other path. We're talking now about the other great lineage, the osteichthyes, or the bony fish. And there's really no debate here. This is, without a doubt, the most successful and diverse group of vertebrates on the entire planet. Just look at that number. Over 29,000 species. And that's just in the modern teleosts. Let that sink in for a second. Their story is just one of unparalleled success. They've colonized literally every aquatic habitat you can think of, from mountain streams way up high to the crushing black depths of the abyss. The result is this incredible explosion of different forms that just dwarfs every other vertebrate group combined. So, what was the secret to their incredible success? It really came down to a couple of key engineering breakthroughs. First up, the swim bladder. This is a gas-filled sac that lets them achieve perfect neutral buoyancy. It's a massive energy saver. And second, the operculum. That's the hard, bony flap that covers their gills. Not only did it protect those delicate structures, but it also let them actively pump water over them. This meant they could breathe perfectly well even when they weren't swimming. So while the vast majority of bony fish, the ones we call ray-finned fishes, were busy taking over all the world's oceans and rivers, a small, kind of overlooked subgroup was quietly working on something extraordinary, something that would turn out to be one of the most important adaptations in the history of life. Let me introduce you to the Sarcopterygii, or the lobe-finned fishes. Now, today, there are only a few of them left. You've got the coelacanths and the lungfishes. But if you look really closely at this evolutionary tree, you'll see that tiny little branch also gave rise to something else, the tetrapods. Yep, that means amphibians, reptiles, birds, and mammals. That's us. These guys are our direct aquatic ancestors. And here is the absolute key. What was so special about their fins? Well, unlike the delicate, spiny fins of other fish, theirs were fleshy, muscular, and supported by a series of really sturdy bones. And these bones had a very specific pattern. One big bone connecting to the body, then two smaller bones, then a bunch of even smaller ones after that. Does that sound familiar? It should. That one bone, two bones, many bones pattern is the exact blueprint for every single tetrapod limb. We're talking a bat's wing, a whale's flipper, your own arm. These fins were, quite literally, the first draft of a leg. All right, so before we follow those amazing fins onto dry land, let's just take a step back and appreciate the universal toolkit that allowed all fish as a whole to become such incredible masters of the water. So what's the engine behind their swimming? It's all in their muscles. They have these W-shaped blocks of muscle called myomeres, and these contract in waves that ripple all the way from the head to the tail. This creates that powerful side-to-side motion that pushes against the water, propelling them forward. It's an incredibly efficient design for generating power. Now, we touched on this earlier, but the swim bladder really is a game changer. By perfectly adjusting the amount of gas inside it, a bony fish can make itself neutrally buoyant, basically weightless. This means it can just hang out at any depth it wants without spending any energy at all to keep from sinking or rising. It's an amazing piece of biological engineering. And their gills, you could argue they are the most efficient breathing devices in the entire animal kingdom. The secret is a brilliant concept called countercurrent exchange. So picture this. Water flows over the gills in one direction, but the blood inside the gills flows in the opposite direction. This clever setup means the blood is always next to water that has more oxygen than it does, all the way across the gill. This keeps oxygen moving into the blood super efficiently, allowing them to pull up to 85% of the available oxygen out of the water. It's incredible. So after all this, you might be wondering, why does this deep history of jaws and fins and swim bladders actually matter to us, land dwellers? Well, it matters because that incredible evolutionary journey that started with these aquatic pioneers, it didn't stop at the water's edge. The path was already being laid out. Those strong, bony lobe fins, they were the foundation. And we can see it happening in amazing transitional fossils like Tiktaalik. Here was a creature that still had fishy things like scales and gills, but it also had a flat skull, a neck that could move, and fin bones that were strong enough to prop its body up. Over millions of years, those fins were gradually transformed into legs, and the great adventure of life on land began. So really, the main point is this. Every single time you look at a fish, you're looking at a living chapter in our own evolutionary story. The fundamental blueprint for our bodies, our bony skeleton, our hinged jaws, our nervous system, even the way our brain is wired, all of it was first forged in the ancient oceans by our very, very distant fish ancestors. All right, let's do a quick flyby of the major milestones we just covered. We started with the jawless pioneers, the first vertebrates. Then came the game-changing evolution of jaws. That led to the sleek, cartilaginous predators, and also to the incredibly innovative bony fish who came to dominate. And finally, we saw how a special branch of those bony fish, the lobe fins, gave rise to all land vertebrates. Okay, time to see what you remember. Go ahead and pause the explainer right here and see if you can nail these 3 questions. All right, you ready? The answers are, number 1, the bony fish, or osteichthyes, have a swim bladder. Number 2, the lateral line detects vibrations in the water. And number 3, the living fish group that's most closely related to us tetrapods is the lobe-finned fishes, the Sarcopterygii. How'd you do? If all this has got you hooked and you want to dive even deeper, check out some of these excellent resources. This explainer drew from them, and they offer a much more detailed look into the absolutely incredible world of fish evolution. But of course, this story doesn't end here. Far from it. In our next explainer, we're going to follow those lobe fins as they take their first shaky steps onto solid ground, kicking off the age of amphibians. Thanks so much for watching.